Hello and welcome to our new chapter. So it's called Inner Product Space, or if you want nice words, you can call that pre-Hilbert space. Hilbert being a mathematician, German or Austrian mathematician from the 19th century. Right. So what are we going to do? We are in a linear space. That's our context. We are always, as always, in a linear space, which has finite dimension or not. And our linear space is most of the time going to be called E. But as ever, you can take a representation when you want to understand what are the notions we're talking about. You can most of the time you can think about R2 or R3 because you can even have a geometric representation of what we are doing. Right. So we are in a linear space. What we want to do is to define that so-called inner product. Another word that we will use indifferently is going to be scalar product. So in French, produit scalaire, we often use the word scalar product to emphasize the fact that the result of this product is a scalar number. In other words, a real number. Scalar is a real number. Okay, and why do we want to do that? Because with this kind of thing, we will be able to define distances and to get a notion of orthogonality, right? And that's very interesting. Okay, in R2 and R3, you already know why it's very nice to have distances and orthogonality. But in more general spaces, it's going to be something that is very important, okay? We want to be able to quantify how far objects are from each other. And you've got quite a few applications here that are given, or you can have a look at those pages to see other applications that you can look at. Okay, so I checked. So Hilbert was German actually, and well, he died in 1943, and he was considered to be one of the most influential and greatest mathematicians of the 19th and 20th century. So that's something. All right. And so pre-Hilbertian spaces are going to be some spaces with some specific properties, more exactly the spaces where we can define this inner product. Okay, so back here. So what do we have? All right, so an inner product, it's called inner product because so we are in linear space E and we take two items. So in E times E, two items, x1 and x2 in E, and we want to find a way to multiply them together. Okay, you've got two items in a linear space, so think maybe you have two items in R3. How would you multiply together two items of R3? Right? So that's an inner product because previously we had to define what was called the outer product, where we would take one item in our linear space and one real number, and that's what is called the outer product because you multiply two things that are not in the same space. Now we take two things in the same space and we want to define a way to multiply them together. Okay, and as I already said, I'm going to call that inner product. That would be more like the general Anglo-Saxon term, whereas scalar product, which is also used but it's more like the French word for it, produit scalaire. That's the word, that's a very common word. And we use the scalar term to emphasize the fact that the result of this product is going to be a scalar number, a real number. Okay, so in order to define a scalar product, an inner product, what is that? That's going to be, well, a map, okay? A map phi, we can denote that as a map phi that takes two arguments in our linear space, so in E times E, and gives you a real number, okay? So it takes, let's say, it takes X and Y in E times E, and it gives you the value phi of XY, which is a real number. okay? And it's going to be a well-defined inner product if it has those three properties, okay? Symmetric bilinear form, okay, positive definite. So, first of all, form, it's a term that we have already used, maybe you've forgotten. It's just a linear map that has its image in R. Okay, so we already said the result would be in R. It has to be bilinear. What does that mean? So, it means that it has to be linear in both its arguments, right? So, you know that for a map, let's call a map F, you know that F is linear if f of lambda x plus y is equal to lambda f of x plus f of y. So that's just linearity. So now we have bilinearity. What does it mean? It just means it's going to be linear in both its arguments. So how can we do that? So we've got one first argument here, that's the x, and one second argument here, that would be the y, okay, and it has to be linear in both its arguments, meaning so it has to be linear if I put a linear combination in the first place of its argument, so phi of lambda x1 plus x2. Second argument would be whatever y, and that has to be linear, so it's just going to be lambda phi of x1 y plus phi of x2 y. And same thing, exactly the same thing in the second argument. So whatever the x as the first argument, if I take a linear combination for the second argument, so let's say lambda y1 plus y2, I want linearity. So that will be lambda phi of x y1 plus phi of x y2. Okay, so you have these two check. It's usually very simple to check. You have to check that it's symmetric, mainly phi of xy is equal to phi of yx. And we can even say that if you show first that it's symmetric, then to show linearity, you just have to show that it's linear in one only of its argument, because then if it's symmetric, it's going to be linear in its second argument. Okay, so usually we can show first that it's symmetric, then that it's bilinear, and thirdly, we need that product to be positive definite. That's a very simple definition. It means that if you take twice the same argument, phi of xx, it has to be greater or equal to 0, and it's equal to 0 if and only if x is equal to 0. So that is usually the hardest property to show, right? So next thing we will have to do is to show that we indeed, given some bilinear map, given some map on E times E with real values, to show that it's a well-defined inner product, you have to show those three properties, okay? And usually the most complicated one is that one, and even maybe that second part, okay? But we are going to take some examples. So in terms of notations, I am going to use most of the time this notation, right? Why? Because it's nice to write and we clearly see the difference between the two arguments. Well, I think it's the clearer notation, but you can use whichever notation you want, and if you are in Rn, you can use the dot product, which works with a dot in Rn, so that's well defined. Okay, all right, so what's next? All right, so now let's give a few more definitions that are just a way, again, those mathematical definitions are just a way to give names to some complex concepts, so that when we say that something is a pre-Hilbert space, you already know what it means. It means that it's a vector space where we have defined an inner product. Okay, that's the definition of a pre-Hilbert space. And if that linear space has finite dimension, this is what is going to be called a Euclidean space. All right? Okay, next video we will treat about those examples, but I advise you now to stop this, well, to pause and try to do it yourself, so that Rn with the dot product is indeed a well-defined inner product that satisfies the three properties that we said earlier. So you can try maybe first symmetry, then bilinearity, but if you show linearity in only one of its arguments and use symmetry, then you have bilinearity. And finally, positive definite. Okay, all right, so try these examples and you can see in the next video if it's all right. Thank you.